So yeah, just a disclaimer, I don't work on color codes in general. This was new. Yeah. So this is work I did with Kavya, Ling, and Ben. So we worked on basically using the using prior work from Kavya to try and adapt it for the surface code and basically correct for depolarizing noise on the surface code better by mapping it onto. Yeah. Is this better? Okay. Nice. But yeah, okay. It's not better. I think it's because I think if I buttons. I have to explain this to me. Is this better? Nice. Oh, okay, I got it. I'm just gonna stay like this. But yeah, okay, so I'll move on since we're a bit late. So for the outline, so I'm gonna briefly talk about the color code and then go through how we decode for the color code using restriction decoder, which is kind of the main way people do when they want to use matching. And then I'll talk about combining symmetries of the color code to correct for bit flip noise. And then I'll move on to mapping the surface code to the color code to try and catch some depolarizing noise. Actually, ignore the one to last point because that's not happening anymore. Not yet, maybe, I will see. Okay, so the color code is a CSS stabilizer code. I think most of you guys are really familiar with this. Yeah, so it's defined on a 3-colorable lattice. Here is just a square octagon version of it. Usually it's hexagonal in most papers. The qubits are placed on the vertices. And the stabilizers are basically products of X Paulis and Z Paulis defined on all the plaquettes of the code. And Y stabilizer is just defined as the product of these X and Z stabilizer at each of these plaquettes. And we can define a Hamiltonian for this code, and its ground space corresponds to the code state of the code. And yeah, so errors on the code create these hyper edges. So I can't point with this, but see over here. So they create, well, they make the stabilizer outcome measurements flip on 3 colors of, well, 3 plaquettes with one of each color. And we also get error strings like the one in example D. But yeah, and the logicals are, they have support on the horizontal and vertical boundaries of the code, or not just boundaries, but strings of errors on the main rows that have D on 2 red squares on them. So yeah, also I should mention there are, so we can associate these defects with anionic quasi-particles. And there's 9 of those that appear here. They all have, well, they each have a color and a Pauli label, and they follow these conservation laws. So first of all, they're created in pairs. So if they have the same color and charge label, sorry, color and Pauli label, they'll fuse to vacuum. And in that table over there, so we have 9 bosons. Is that right? Yeah, and they, for each row and each column, they will basically, well, pairs of them will fuse to the 3rd one in that row or that column. And that corresponds to these conservation laws here down there on the slide. So next I'll talk about symmetries of the color code. So this isn't specific to the 4881, but that's the one we'll be looking at later. But yeah, so they give us a nice way to interpret syndrome data. And symmetry is defined as like this. So it's a subset of stabilizers of the code, such that when you take their product, you get the identity. Or yeah, equivalently, like derived from that, if you take the product of their eigenvalues, then you get +1. So that kind of implies that you'd have an even number of defects on the symmetry of the code. And the symmetries we're interested in correspond to basically stabilizers that have support on plaquettes or on pairs of colors of the code. So here I show a red symmetry. This is taken from Cavia's paper with Ben, actually. And this is just something equivalent for AH code. And yeah, so we've removed the red plaquettes, so we don't detect the red syndromes. And here, the red line that's going through the edges between the red plaquettes is a logical Z operator. And we see that error strings that are created, that cross this logical create an odd number of defects on, the number of defects on each side of this string will have an odd parity. Yeah, and so we basically use that to determine a correction for the code. So normally, yeah, I mean, if you look at this, you can kind of see that the parity of the number of errors that like share locations with the logical should be equivalent to the number of crossings going through the logical once we've run a matching decoder. If we have a right correction, otherwise there will be a logical failure, and we can apply a different correction to that, just flip that value, I guess. So yeah. Okay, so people usually decode on the restricted color code using matching by basically taking restricted symmetries of the code. And then that kind of is equivalent to matching on the surface code. It recovers the same threshold, so it's pretty nice, it's pretty high. And yeah, so this is basically the approach people take. You can, usually, yeah, you'd match on the different restricted lattices, or two of them, and then you'll infer kind of, yeah, try to infer some correlations. But yeah, you can't get more than this, I guess, with the restriction decoder. Okay, so earlier, I should go back here. So this was defined on an infinite lattice, or a lattice with periodic boundary condition. And so the symmetry was okay to be defined this way. But if we include boundaries, then these products of stabilizers and those symmetries no longer give us the identity. And instead, they'll give us a boundary operator, like the green boundary and blue boundary shown here for the square hexagon code, sorry. And so these boundary operators are just defined as the product of all of these faces of the symmetry. Yeah, well, it's not a symmetry anymore. So yeah, they're defined as all these the products of all the faces that have a color not equivalent to the color indicated by the boundary operator. And so now a new symmetry that we can use for decoding requires including the boundary operator in the symmetry. So for each color, so it's just a color label. Yeah, we define the symmetries this way. And then, yeah, that just implies that we can now match defects at the boundary. Yeah. And also we can see that if we take the product of the boundary operators, the red boundary is not super obvious on the square hexagonal code, but I mean, it's just basically at the corners. So if we take the product of that, we get the identity. So yeah, nice symmetry again. And so like we said before, the symmetries of the color code correspond to this like charge, or sorry, I'll say, what's the word? Yeah, defect conservation law. That basically says that, it tells us that the parity of the number of red, blue, and green defects on the color codes is equal. But yeah, from that, we also see that, yeah, if we have an error in the bulk, and we apply a boundary operator to the state, then it shouldn't do anything because the boundary doesn't have any support on the stabilizers inside the lattice, in the bulk of the lattice, sorry. So errors at that boundary will violate the global defect conservation law of the code. And we can see it here. The top one should be at the corner. It should come from the red corner. But essentially, you see that now if an error happens at the boundary, then, for example, at this green boundary here, then we'll get a defect on a red plaquette, a blue plaquette, but not the green one. If it happens in the bulk, then we get the 3 edges. And at the corner, we'll only get one red defect happening on the red square. So now that means that when we apply this boundary operator to the state where an error on the boundary has happened, for example, then yeah, applying the red boundary operator, blue boundary operator is equivalent, but not with the green one. And so this tells us that on the green-blue and the red-green restricted lattices, which just means, like respectively, the lattice where we remove the red stabilizers and the blue ones. Yeah, if the defect parity conservation law will be violated if an error happens at the boundary or from a green corner, yeah. So yeah. So basically, this tells us that, yeah, considering these defect configurations on restricted lattices separately, which we have to do when we use the restriction decoder, will cause some corrections that violate this boundary symmetry. And that's not the most helpful, and we can do better. So that's what was shown in the work by Kavya and Ben. So yeah, they basically just took all these symmetries of the color code and glued them, making sure that the boundaries have to match. And yeah, so the idea is that now you see at the boundary, we don't have this violation of the defect conservation law anymore. And so this should hopefully give us some information to match better. Well, that's what they should. So we can catch more errors this way. Now, something that came up in the paper that also comes up for us is that we have to figure out how to assign weights to the edges of the graph, the matching graph of this new lattice. So here, the intuition they took was that, okay, in this new lattice, errors don't map really trivially across the lattice. So if an error happens at so actually, I should specify so going over one boundary to the right and to the left is a reflection. And the qubits at these corners are unified. And this is actually referred to as the unified lattice. And essentially, an error in the bulk of the lattice will create 3 edges now, since we have these 3 different lattices that are stuck together. An error happening at the boundary is going to create 2 edges, and an error happening at a corner will create a single one. So the strategy to weight the edges in this case was to set an edge in the bulk to have a weight 1, and then an edge on the boundary to have a weight 2, and on the corner to have a weight 3. And with that, they showed an improvement in the number of correctable errors they can catch, and also improvement in threshold. But that didn't work for us, actually. But yeah, so the decoding procedure is kind of similar to earlier. You run minimum weight perfect matching on this new lattice, and now the logical operator is going to correspond to one of these creases between 2 glued restricted lattices. And so it's the same principle. We count the number of crossings we get across the logical operator, and we compare the parity of that with the parity of the number of errors that have support on the logical. So yeah, and this is nice because so there's no color dependence when we choose, because we don't have to choose which lattice to pick for the way we do with the restriction decoder, and it's invariant under color exchange. So we're looking at decoding on the unified color code on the square. I said square hexagonal earlier, sorry, it's for square octagonal lattice. So for us, it's going to look like this because, as I showed earlier, we have these blue boundaries blue vertical boundaries to the right and the left of, for example, the blue-green restricted lattice in the middle, and the top and bottom boundaries are green. So we match them to these two restricted lattices. We have red, blue on the right, red, green at the bottom. The logical operator, just for now we take to be, well, without loss of generality, I guess we take it to be logical Z. So we consider all Z stabilizers and a bit flip noise, an IID bit flip noise model. So yeah, again, same principle. This lattice is now associated with this global symmetry that will respect the defect parity conservation law at the boundaries. And yeah, the idea is that we can catch errors just like we could with the unified lattice, but with the unified hexagonal color code. But calculations are a bit more tractable here if we want to kind of quantify that, because we don't have branching errors, like branching logical errors, and yeah, it's just a much easier lattice to consider. Its boundary conditions are shown here. So it's essentially a torus with a hole in it. So yeah, we basically considered, after a lot of trial and error, this matching graph with these weights. We started off with weight 3 at the corner, 2 at the boundary, and 1 at the bulk, just like the hexagonal case. But we ended up having errors at the corners that were basically avoiding the lattice at the bottom. And so, yeah, basically, this correction here is what worked for us. Others would work as well. That's the thing that was tricky with weighting the graph. But yeah, so this is what we're going to work with for now. And yeah, so we want to estimate the logical failure rate at a very low physical error rate. And in that regime, it's going to be dominated by the number of minimum weight uncorrectable errors. And that'll be errors of weight D on 2, where D is the code distance. Yeah, because yeah, the color code here is always even, as you can see. And yeah, so in order to count these errors, so here we consider the restricted lattice. Since we have one color that's gone, so here's the red blue restricted lattice. You can see how strings of D on 2 errors are gonna affect the lattice. And so here, for example, a string of horizontal Pauli X operators on yeah, D on 2 squares of the lattice are gonna give rise to the syndrome. So you see that the decoder wins with half chance. So here, oh yeah, I should specify the green and red X labels just show us errors that produce the same syndrome. And so yeah, in this case, the 3 of these are failures. So we need to consider basically all of these type of explanations when we count how many uncorrectable errors we will get. So we know that, so yeah, first we kind of count for each row. We know that for each square, there's 4 possibilities for pairs of bit flip locations, and 4 possibilities for single qubit locations. And so then we just count essentially if we have m minus 2k weight 1 errors given k weight 2 errors, then on each row that has m plaquettes on it, where m is D on 2, the number of number of uncorrectable logical errors is given by the sum over there. And then, yeah, we just take half of these and multiply by the number of rows. And that gives us the numbers over here. So here in this table, I just show for low distances, the estimate here and the, which corresponds actually to the numerical test we did. So it was just an exhaustive search where we just generated all D-on2 possible errors, all possible errors of weight D-on2 on each one of these rows supporting M plaquettes. And yeah, we just checked that we got the right thing. So this was the case for the restricted lattice. And then moving to counting minimum weight failures on the unified lattice, we see that we have an advantage now because
So on this middle error, like this one thing,
this one?
Yeah. So like this,
yeah.
This middle logical error with the text that goes through the diagonal, they're making green syndrome, but they're not showing up on the illustrations. So that means all the green dots. And we should be able to correct this for that station.
Yeah, exactly. So if we map the error onto the unified lattice, then we do get these green syndromes on the green stabilizers. And now running minimum weight perfect matching will give us a blue correction that's correct. So yeah, that's basically that example. I mean, it's the same error, but on the other side. Well, more or less, it's two diagonal errors. Yeah, exactly. So because we can, because we have this advantage from these diagonal errors, we ignore them in the calculation. And so we just consider the single qubit locations on the red squares and the horizontal 2-qubit pairs. Sorry, 2-qubit locations on the red squares. And then, yeah, it just changes our factor of 2 to the power of k to 2 to the power of k now. And yeah, so this is our new count. And you see that, yeah, I mean, it drops. And this is from the numerical simulation. So again, it matches, yeah. So now the idea is to use this unified lattice, but on the surface code. And I think, yeah, I'll briefly go through this here. So just to motivate this, the idea is that if we can map depolarizing noise on the surface code onto a bit flip noise on the color code, then yeah, we'd be able to catch these correlations, well, the Y errors essentially. And that's kind of the motivation of this. So I'll show the mapping in a second, but yeah, this is basically the motivation, right? So if you have a string of ZY, Z errors on the toric code, then if you take a restriction decoder, or well, no, I call it a restriction decoder here, but yeah, pretty much. If you decode for Z and X errors separately, then here, if your decoder gives you this solution plus this solution, you end up with a logical error. But if you get this one and this one, then you'll get the right one. So the idea is to kind of get this from the beginning with the mapping from the surface code to the color code. So again, everyone I'm sure is familiar with the surface code, but I'll briefly go through this. So it's also CSS stabilizer code defined on a 2-dimensional lattice. Each edge has a qubit on it here. And yeah, so the stabilizers are these products of Z Paulis on the squares and of X Paulis on the stars. And the anion model on the color code, sorry, on the toric code has 4 charges. So vacuum is E and M, and E and M are bosons, and psi is a fermion, which corresponds to the fusion of E and M bosons. And so there exists a mapping between the color code in 2 dimensions and 2 decoupled copies of the toric code. And this kind of translates into this mapping of the anion models. So if we take two copies of the toric code and consider like the anions on one of them and the other one of them, so we can basically recreate the like 6 fermions of the color code from the fusion of one boson and one fermion from each copy of the toric code. So this is just an intuition basically for the mapping. Here in this table, it just shows how we get the color code anions, like the generating sets of anions that I showed earlier. And you see that wherever vacuum shows up, it means that we have only one charge on one of the toric codes, not the other. And then the cross in the middle is when we have an anion that's composed of anions on the 2 layers. So a bit more concretely, this mapping kind of can be constructed as some kind of local Clifford unit tree that would take the color code and kind of disentangle it so that its stabilizer group would be transformed onto two stabilizer groups for each copy of the toric code, which would have qubits, which have support on different qubits of the color code lattice. So this is basically an explicit construction. These are a few papers where these types of things come up. So the first one and the second one. The last one is a bit different. So the idea is that each red square, we kind of shrink to a vertex. And then the first toric code is going to have its edges going between the red vertices so that at each stabilizer of the color code, so at each octagonal stabilizer of the color code, we're basically going to kind of make that one bigger, and that will become one stabilizer of the corresponding toric code. So for in the blue case, for example, we will take the blue stabilizer and so we just basically match, we create edges between its center and these vertices of the red plaquettes, and here as well. And then from that, we kind of construct the lattice, and we see that these will be the faces of the this blue toric code, so the first copy. And equivalently for the second one, we will get kind of a rotated version of that. So now the way errors map is that, so here we actually only consider still just the Z plaquettes of the color code later on. But what matters is, so these are the plaquettes of the first and second copies of the toric code. And an X error on the toric code is bound to light up the 2 Z stabilizers. So it kind of indicates, the 2 Z stabilizers of the blue toric code and the two phase stabilizers, Z stabilizers of the blue toric code, and the 2 star stabilizers of the green toric code. And so the top row and bottom row just happen at different places in the lattice, essentially. So this one over here would happen where the blue and green toric codes cross in this direction. And the other one would happen, for example, at the square in the middle of the lattice on the left. So we can basically map X error, Z error, and Y error on the surface code or toric code onto these pairs of bit flips on the red stabilizers of the color code. Another picture that's a bit more intuitive is that we can kind of get the same code mapping by concatenating the 422 code with 2 copies of the toric code. And then these errors here kind of come naturally from the logical operators of these gauge qubits that we would have at the locations of the red squares. So now that we have that, we can count the number of failures that we'd have on the restricted toric code with even distance. So yeah, in the case of even distance, we care about errors of d on 2 weight, and the errors that will affect us basically and create these potential logical strings are the diagonal ones and the horizontal ones. So that would be the X and Y Pauli errors. And so yeah, we just count basically combinations of these on, actually, this is not an even color code. So this is not an even toric code, sorry. So imagine there's one more square. And then yeah, so we look at these configurations on d on 2 squares on each row. And that gives us this expected number of failures in the middle for distances 4, 6, and 8. And they're matched by the decoder on the right. Oops. Okay. And in the case of the unified toric code, so the same argument that we had earlier happens where now the diagonal errors we're able to correct for. So we only consider the horizontal ones, sorry. And so we lose that factor of 2 to the power d on 2. And that'll give us an improvement of approximately a half to the power d on 2. So exponential in the distance, basically. So yeah, that's kind of what we were looking for. And here again, it's just the number of failures. Here I split them by rows because it gets a bit trickier for the odd distance toric code. But yeah, in the case of the even distance toric code, we basically catch them all. A distinction is that, so here I use the same matching graph as we did for the color code earlier. But when we move on to the odd distance toric code, things are a bit different. So now we consider logical failures. Well, we consider, sorry, minimum weight uncorrectable errors that would have weights d plus 1 on 2. And so we want to count, again, an estimate for these. And we would, yeah, this is what we would get. I mean, that's pretty straightforward, I think. This time we can kind of see it since we have a distance 3 toric code mapped on a distance 6 color code here. And oh, I think I forgot the table here, but the decoder matches for the restricted toric code. Yeah. Now, if we take, yeah, so first I should probably, so this is the matching graph we used, but I think I should kind of motivate it a bit afterwards. So I'll just start by considering the odd distance unified toric code, but mapped onto the unified lattice. And in this case, things get a bit tricky. So we have to account for different types of errors. So the first type of error is, errors of d plus 1 on 2 x errors on the toric code. So d plus 1 on 2 horizontal pairs of bit flips on the color code distributed on the red squares. So these already are going to make our decoder fail. This is expected, and we count them. It's d to the, d choose d plus 1 on 2. Second kind of error that we consider is actually has a y error in it now. So yeah, I should have made this a bit more clear by showing you the correct and the, well, you can guess the correct matching just by looking at the error configuration, but the wrong matching. The wrong matching essentially goes through the logical operator in the middle now, and they will have the same weight. So yeah, so we count these on the left, and so yeah, we get these errors extra, and they correspond to d minus 1 on 2 x errors and 1 y error on the toric code. But we also have an alternative scenario that creates the same syndrome, and so these kind of have to be counted all together. So yeah, we'll have the same number of these, but in total it'll contribute exactly and fail B over there. And these correspond to 1z error on the toric code and d minus 1 on 2 x errors distributed this way. And then we have a third case where we have 2 y errors on the toric code. Again, actually, I should have said, but it's pretty obvious. They're yeah, the case 1, case 2, and yeah, actually all of these take place on one row. And so we count these on the left. And again, we can get a similar syndrome where now we have a pair of qubits on the row just above it that are contributing to this. And yeah, so again, these have to kind of be considered together. And in total, we'll get the NC fail contribution from them. And so if we add these 3 cases, so 1, 2, and 3, and their alternative possibilities, we get these expected number of failures in the middle. And these are the ones that we get is just up to distance 7 here. So already at the top and bottom row, we get some extra failures that we don't like, and we need to get rid of them. So that's what motivates the choice of the matching graph. So before, what we were using was this matching graph, except the red edges also had a weight B. And that created errors of this type on the left. So here I show the correct and incorrect matching configurations. So you see that, yeah, the blue one avoids, the blue one crosses the logical through this corner right here, when the purple one doesn't. And to be able to catch these errors, we basically need to make it a bit easier to kind of access the green-blue lattice, and also actually red-blue, but mostly green-blue, by setting the red edges to 0. So that's a trick, but actually I found that other weight configurations help us catch these errors. But they just make things a bit tricky with another class of errors that I'll briefly mention later, but I won't go through. So this is an equivalent error, but happening at the bottom of the code. So yeah, it's a bit clearer here what the matchings look like, but now we can catch them with this trick. And now that we've done that, we can get the expected number of failures, down to this many for distance 7. I checked up to distance 11, not more than that. But we have some remaining errors actually that we didn't, well, this is a courtesy of Ben, this is me. We tried to count them and figure out how to catch them with the unified lattice, but it's tricky because when you can correct for them, you end up not being able to correct for some of the other ones that we had in this case. So yeah, we're still thinking about that, but we'll see what happens. But yeah, so that's basically the gist of it. Most of my data is running the cluster. I haven't been working on this for a long time. But yeah, just a few results at low error rates, so between 2% and 5%. This is, and for quite small distances, is how the restricted and unified decoders perform for bit flip noise on the color code. So here is an analytical expression just from the fits up there using the ansatz p-fail over there. And so we see that basically below 5%, the restricted decoder performs much worse than the unified decoder. Yeah, I don't know exactly why the crossing happens here, but yeah, it's some entropic contributions that become much bigger, I guess, because we have the unified decoder being 3 times the size of the normal restricted decoder. And then threshold estimate, again, small sizes, not much data, but yeah, the restricted decoder recovers 10.2%. And in the unified lattice case, we don't get an improvement. So I tried varying the weights A and B in the matching graph. Yeah, so this one, for example, I varied them for both color code and toric code. But yeah, we couldn't get an improvement, but it looks like we can get up to the same threshold as the restriction decoder. So there's that. This is also restricted. This is, yeah, pretty bad threshold fit, but needs more data. For the Tory code. And yeah, these are missing, but they will come. So just to wrap up, yeah, we basically propose a matching decoder for the surface code that would be able to catch depolarizing noise errors using the color code unified lattice trick. Yeah, we have analytical arguments, and we did some exhaustive testing to show that we can do better. We get an exponential improvement in the code distance. And yeah, some open questions we have left now are basically, can we count? Yeah, well, we need to count those errors. I think, yeah, we mostly have, but the errors that are distributed on 3 rows. And then maybe, yeah, see if we can find a way to correct them by playing with the matching graph. And yeah, another question was basically how to take advantage of these symmetries to correct for depolarizing noise on the color code, which was mentioned in one of the appendices of Ben and Kavia's paper, but still not clear yet. Yeah, I think, yeah, that's it. Okay, I'll stop here.
Questions? So I think I'm asking to speculate that you were saying at the end, I mean, you're looking at the logical error rate for effectively very sufficiently low error probabilities, and then you can count things and see that the decoder is optimal. And then it seems as though there's a topic that is close to threshold, meaning the threshold is very similar for these decoders and less sophisticated decoders. So those, do you have a sense of where those behaviors cross over?
So I think it should be around that point from the ansatz, because when I overlap the numerical data, it's around 5% physical error rate basically.
Oh, so I was going to ask about this. So these curves are analytical. The orange and the blue.
Yeah. So these curves are just the failure probability, logical failure probability up there. So it's an ansatz, but for that I use the parameters for the restricted and unified decoders here that I fitted to this numerical data. And so overlapping the numerical data also gives some kind of crossing around 5%, just a bit below 5%. But yeah.
And capital N there is that's part of the fit, is that right?
Yeah, exactly.
Matthew. Can I ask something which set up this unified ladder? So color code unfolds into the color code, but here you're unfolding white. What's the difference?
That's a good question, actually. Yeah, I guess you're unfolding twice, but also they're matched at the boundaries. I haven't actually thought about the boundaries much of the restricted lattice. So yeah, like these aren't like decoupled Tory codes, right? Or actually, no, it's not true. They have to be because we mapped onto the, I don't know, it's a good question. Ben, do you have an answer?
These are two different things. So yeah, the color code is fucking color code, but you don't. I want to conflate those with the different symmetries. There are two different. Yeah. So I think you can really like two color code copies with two of those symmetries. So the third symmetry is associated with the two. So in this restricted lattice, sorry, this unified lattice, the folding map is quite different.
Yeah. So great job, thank you. The method is good for depolarizing noise because the Y errors, well, I take it because the Y errors sort of like correlated errors. So are there other types of correlated errors that this would be useful for?
That's another thing that would be really fun to think about.
The one thing that's a little funny about this decoder is you don't even use any of the red states.
Yeah,
And under the mapping, X errors, Y errors.
exactly.
Y errors. So no errors in the mapping layer of the red state. Like,
So that's also why depolarizing on the noise on the color code would be potentially solvable with this. Yes.
Then I just asked, you reminded me, you might just ask the question. So the reds, in the end, you had the red, some red lines stop weight 0. And so in this weight that you gave, there's this graph, you that choosing some weight shows the red lines to weight 0 in the photo.
Yeah.
And I suppose I was just perplexed as to how that wasn't that logical choice, but that is to do with the fact that the red squares don't get lit up by any of the errors in the error model.
Let's see, yeah.
well, something, yeah, but you never match anything to that. Yeah, you're right. It's one of those lower blue ones on the blue-green ladder. Might match to a green one just beneath it. So it has to go through 2 edges. One of them is 0 weight. The blue one is not.
That's right. So there's no error that's been terminated on a red
No,
square.
never.
So only one into both red lines can be better.
Something like that, yeah. I think this is a weird technical trick. It's kind of hard.
Yeah,
to get the other two, but it's like, this is the catch, like the last.
yeah,
You ever-
but it can be avoided actually. Yeah.
The ones that are going to those red state like this, basically anything that goes to red state like this. Only. Like there could be a path that crosses the red state like but it doesn't end up in the red.
Yeah, that one, you never finish on it. So sometimes you go through 2 edges too. Right, in fact, nearly all the time you have to take 2 edges. Yeah.
Just makes, yeah, the crossing from blue to green shorter, but the reds don't really matter there. Yeah.
Any other questions?
Is this way of decoding like qualitatively similar to what you would get if you also measured products of X and Z as fermions and then use that symmetry as well as the symmetry of EM? You would have like 3Z2 symmetries directly on surfaces. Seems like kind of what you're doing.
So what would happen if you measure the fermion symmetries?
You would just have like a growth matching mathematical ties of the other two boundaries of this.
So how would that be different from decoding on the restricted lattices separately and then trying to like kind of infer this? I think yeah.
I think yeah, they end up getting tied together at the boundaries. Then
Yeah, okay.
I mean, what's a bit weird? So the way you should understand this mapping is the blue stabilizes with stars. So you kind of like a regular vertical star because it's on the right hand side, and the green ones are for cat. And what's funny is this thing in the middle lets you add east to end.
this is up
Yeah, that does all kind of, well, that does kind of like, I mean, the point is to get a logical error. You have to make strings that go through the regular vertical decoder, it's like augmented by this blue green part as well. And it turns out that no P, that's quite useful. But as Andrew asked, and as they mentioned, when P gets a bit higher and you get a threshold, it makes more, that's more than it helps.
Wondering if there's both. You said that the red stabilizers never light up. So you're not using those red stabilizers to just mapping. I'm wondering if there's an alternate mapping where you could use the red stabilizers. Essentially, like in any code when you have bias noise, you are able to use more stabilizers to decode errors like this. Makes it better. both of those were specific. I'm wondering if this could be, if there is a mapping where it would use the best left also and get a better.
I wonder if there is a bigger, like, I wondered if maybe you could put some flagging information on there or something.
Yeah.
Or, we haven't done that. I think it's a cool idea. Like, I'm trying to like, I remember what's the trick here, like, we're trying to do those things several times in several different ways. And taking them all together end on end, keeping with that or something. Yeah, it would be interesting if you had other Charlie there. I don't know, but that's a cool idea.